Yeah, thank you. Thank you for having me here, and really delighted to be here to give a talk and participate in this event. It's great to see so many students here. I understand that it seems like you also have to be working very hard on your TRB papers, and I will try to help facilitate that as well. So some of what I'll talk about, especially in the second lecture, will be brainstorming ideas with you. That can be applications of the material that I'm covering today. I understand that timing-wise, maybe it's a little bit late now. There's only a little over a month left. But a true story, my co-supervisor at UC Irvine, Professor Jay, one time he thought of an idea and he worked overnight and it became a paper that went to TRB. So it's possible, anything's possible. So we'll see how that goes. So the topic that I'm going to present today is on modeling mobility as a service. Right. So the idea, the topic is essentially looking at multi-operator ecosystem settings, right, where you have an area where there are different mobility operators that might be competing, that might be collaborating to provide service to travelers, and trying to understand how we can analyze those kinds of systems. Right? So this is just a graphic of different types of mobility on-demand markets that are growing very rapidly. Right? So in the top figure, we see microtransit and ride-pooling markets around the globe, and I believe even in this one, there's already some services from I think Studio Galilei is already part of this market growth, but other enterprises like Via in the U.S. and then in Europe, there's a lot of other types of services available. You can see it's growing quite rapidly. There's other micromobility as well, so bike share, e-scooters, those types of services are also growing rapidly. And this is all growing not in a vacuum, right? They're growing in a space where there are other competitors. They're growing in a space where they might have to work with other mobility providers, maybe as last mile services for fixed route transit, right? Or trying to provide like vehicle sharing that can also make use of shared space at mobility hubs, as an example, right? And these are also driving a lot of the different technologies that we're seeing right now, right? So there's the automated vehicle discussions that came in previous talks, electrification, and also shared mobility. So there's this convergence, and a lot of transportation researchers these days are looking at that convergence. Along with those technologies, we also see a wide variety of different types of operations, right? So I mentioned first, last mile, but also in deliveries. So crowd shipping, looking at carpools, to school or healthcare access. The applications are quite widespread. It's not just commute. It's a lot of different ways of providing mobility services to people. So the mobility as a service, or MaaS angle that we talk about here is the idea that with all these different types of services in this ecosystem, how do we organize them in a way that can be more beneficial to society or to the providers of these types of markets, right? So this I really like this graphic because it kind of highlights the wide array of different technologies that have to be considered. Right? It's not just mobility; it's also information provision, financial transactions, ticketing, infrastructure. So there's a lot of different pieces to this puzzle, right? And there are some trials and pilots and some success stories, but also many failures, right? So one of the biggest failures more recently, I think the company WIM, or the company Global MaaS, they produced this tool, this MaaS tool called WIM, and even that ended up going bankrupt recently, to the point that some researchers don't really believe this can succeed anymore, right? That this could be a failure. There are some success stories though, as I mentioned, and I know there's a pilot recently in Australia that's looking like there's a lot of potential. There's this pilot that was operated in Pittsburgh, Move PGH, right? That try to combine different service providers together. So there's a lot of these kind of coalitions forming between different mobility providers to work together to provide services. But the challenge really is when they try to design these types of platforms to operate them, the question is how do they how do they make it work, right? So trying to really understand the shortcomings or the limitations of these kind of designs is a tough problem, right? And this problem is due to a couple of different factors, right? So when we think about the system design aspects, there's from the point of view of the mobility operators, they're thinking about what kind of lines they want to serve. If they're fixed route transit service providers, it could be looking at the fleet size that they want to provide, which routes they want to serve, what service region, and different types of policies for connecting with passengers through fare payments or through other mechanisms, right? Maybe, for example, in the US, the company Via, they've designed these virtual stops so that people would have to walk a little bit more, but it would cost Via much less to operate their routing to accommodate those services. Right? So finding those kinds of trade-offs, how do you actually analyze that? From the perspective of the platform provider, or in many cases, this platform provider could be private company like Uber, right? But it could also be a regulator like a public agency, right? So for them, they might be thinking about how do they manage the infrastructure to accommodate these kinds of services, right? And how do they subsidize these cases to make it work? Right. The transport planners traditionally, assuming we're all transport planners here, right? We want to know what's the ridership on different services. We want to know what's the impact on the social welfare, right? What's the impact on accessibility, on equity, and looking from the regulatory perspective, we want to be able to determine what level of subsidies are really needed to make these kinds of systems operate. And it goes pretty far-reaching, right? It's looking at scenarios like urban air mobility, using that as a piece of a puzzle to provide last-mile services, let's say, or looking at the impact looking at the impact of subsidizing first last-mile mobility on-demand services from terminal stations, from fixed route transit. Right, or determining like delivery prices when a new crowd shipper joins the market. What's the impact on the rest of the market as well? Right? So all these kinds of decisions are hard to right now for transportation planners to model and analyze. Right? So that's where we've been working for the last few years to try to develop frameworks that can understand this better. Okay, so. Essentially, if we think about transportation modeling from a more traditional point of view, the way that we model transportation systems to answer those kinds of questions traditionally has been looking at these as kind of like looking at planning models, right? Like, for example, trip assignment, traffic assignment models that would predict based on a certain amount of demand for different origin-destination pairs, how that ends up translating into ridership or volumes on different links in the network. So I'm going to start just by covering a little bit of network assignment. Right? I'm sure this is pretty familiar to you all, but just to start on a common page. Right? So this is the model formulation for Beckman's traffic assignment problem. Slightly modified, so it's not just, so you might be more familiar with just looking at this piece of the objective function, right? Assigning the flow to fill in, essentially, if you think of the cost functions as these monotonically increasing costs, it's trying to minimize the area underneath them, right? And the difference here is that we also have, so we have essentially these are flow variables along the different links expressed as path variables. We have link costs, we have link tolls, we have demand, inverse demand function, so that this is a variable demand formulation. Right? This was already in Beckman's work. They already had a variable demand formulation back then, right? So I wanted to show this because this model would then output for a given demand function or inverse demand function, it would output the amount of ridership on the different links of the network that takes into account the congestion effects, right? As an example, if you have an OD pair like this with two parallel links, with these as your link costs, considering the possibility of tolling them, you can write this out as this nonlinear programming problem, solve this, right? And you would get these flows, right? You would get these toll prices, these flows, and the equivalent generalized travel times that would match, right? That's the UE principle. And the neat thing is that this would then correspond to the system optimal flows. So if you solve this as a system optimal problem, the flows from this problem would match with that, right? So that should be familiar to most transportation modeling grad students, right? And the thing I want to emphasize here is with the UE assignment, with pricing, you can achieve system optimality, right? Or equivalently, you can look at this as a system optimal assignment can accommodate user behavior when pricing is allowed, right? When there is an exchange between the operator and the traveler. This BMW model also assumes all links are owned and operated by a single operator. Right, so those are the two key points I want to bring up here, right? Because we're going to change some things. We want to look at these ecosystems now, where the links are not necessarily all owned by one person, one agency. They're owned or operated by different operators in an ecosystem, which each have now their own incentives as well to operate this service, right? Whether or not it can profit for them. Whether it makes sense for them to serve one route versus another, right? And the framework here is looking at using an alternative way of thinking about things, basically matching operators with travelers, but in a way that you'll see that it aligns with what you've learned before with user equilibrium modeling, with traffic assignment modeling. Okay, so in this setting, the problem is more complex because when we start off with these centroids where we have demand, we have also different routes that might be served by different operators. So here I'm using different colors to represent different operators, right? Green and red. There's additional links that might be representing either access or like links that might be transfers or access that nobody owns, is just a way of keeping track of the cost for them. But also there are alternative dummy links, that we'll call them dummy links, which represent the option of not participating in the system. Right? So these people might be telecommuting, they might be they might be driving and not using any of the services being provided by this ecosystem. Right? So it captures all those other alternatives. Okay. We also have these operators considering service regions that might be providing on-demand services, right? So these are like real-time on-demand services like Ubers and Lyfts, taxi services, as well as all the micro-mobility and other modes that I mentioned earlier based on real-time data, right? And in those cases, those are very stochastic dynamic operations. But here we will treat them as a steady state consideration. So we're looking at the steady state of these types of systems. So there's cost functions that we can use to model the wait time or meeting time for a traveler to get onto one of those vehicles to go from place to place, right? And so these operators are deciding where to serve and maybe how many vehicles to serve in the fleet, right? So different fleet sizes might be considered. So that's the scope of the setting that we're considering, right? And so how do we try to model that as an assignment problem? So we look at stable matching from platform economics. So early on from cooperative game theory, we have these ideas of stable matching between different, from buyers and sellers, right? So you have buyers P, sellers Q, and you try to find matches between them such that no agent has an incentive to break away. So the agent could be a buyer or a seller, right? And in the special case where the utilities are known, continuous, and transferable, the problem becomes an assignment game, right? Where it assumes that you know the utility for the match between the buyers and the sellers at a certain cost to the seller that can then be relayed back to the buyer through cost transfer with a payoff. Right? And so the matches are binary, right? You're considering single buyers, single sellers, one-to-one matching in the basic case, and you can get the payoffs through this computation. And they provide a model formulation for this, right? So it's essentially an assignment model for the matching part, right? Where you have a linear program, right? You can relax this because of union modularity. So you're trying to maximize the payoffs to matching them in a system optimal manner with the understanding that they will transfer costs. So it's possible that they can achieve the user behavior incentives, right, under the stable matching, right? So for corresponding to this, for those familiar with linear programming, right, this is essentially like a primal model with a dual model representing the payoffs that they can get. Right. So that's really nice because this implies I can solve an assignment problem and I can get the corresponding payoffs between the buyers and sellers using the duality conditions. Okay. So this problem as a one-to-one assignment problem is simple enough that it's guaranteed to be non-empty. So when you solve this for a given problem, you'll always be guaranteed to have a solution, a stable solution, at least one, or if not more, right? So that's a nice thing because then you don't have to like try to add additional constraints to this explicitly to get that kind of solution. And in the case where you do end up with multiple possible solutions, and I'll show an illustration in the next slide, you can then find extreme values, so like at the two ends of the space, right, of how much pricing you can allocate between buyers and sellers. You can allocate based on a buyer optimal case, which basically is setting the allocation so it benefits the buyers primarily, or the seller optimal case, which benefits the sellers primarily. Right? So there's two different opposing sides to it. Right? So as an illustration, we look at assignment game for housing, let's say. So here you have three sellers selling houses and three buyers looking to buy houses. The sellers have these costs associated with each house, and these are the amounts that each buyer values each house, and they value them differently, right? So if you try to match them, you would get something like this, where this is the optimal matching, where this 8 is basically 26,000 minus 8,000, right? It's in thousands, right? So this would earn you the most payoff with these three assignments. Buyer 2 to seller 1, buyer 3 to seller 2, and buyer 1 to seller 3. And corresponding to this assignment, there's different amounts that can be exchanged between the buyers and the sellers that would make this stable for everyone, right? So this is one possibility, but there's others. So if you map out the space of what's possible for exchanging between the buyers and sellers, any solution in this polyhedron would work, would be a stable matching solution. Right? So this kind of problem is looking at trying to optimally assign a matching between buyers and sellers, and then in a way that allows us to determine whether or not there's feasible or stable pricing that can be associated between the buyers and sellers, so that they have the incentive to stay that way, right? And that's what we think can be effective for applying to mobility as a service system, because in that case, we're looking at how we can assign travelers into the system as flows, but in a way that also allows us to determine mappings of the pricing, the cost allocations from the travelers to these different operators. Okay. The challenge with taking that simple framework that I just showed in the previous slide into the mobility as a service is that now we're dealing with these path flows, right? So instead of one-to-one matching as we see here, we have more complexity. We have different user groups representing different OD pairs, or even OD pairs and population segments. So you can have low-income people from node 1 to node 3, high-income people from node 1 to node 3, like centroids, with a certain amount of demand and expected utility that they gain for achieving that trip, and then choosing different paths to take. And you have different operators that own sets of links that are deciding whether or not they want to enter the market, how they want to enter the market, what kind of fleet size they want to allocate, what kind of capacity do they want to allocate into the system. And it turns into something like this, from this to this, right? Because now you have path flow, the paths for the users, you have operators deciding on which links to serve, and this goes from a one-to-one matching problem into a many-to-many matching problem. Right? So that's one of the complications of this framework. This is what Sotomayor calls multiple partners game, but with the additional network effects that we have in our case. All right, so how do we model this? We start just looking at fixed route, for example, initially, right? So when I say platform, I'm referring to this whole ecosystem, right? So we have this ecosystem with the one regulator managing this platform, and it's matching these operators to these travelers. And so these could be centroids, and you have station nodes, and the links might be operated by different mobility operators. They have different costs. So I use a triple to represent this. So the first is the travel disutility for the users. This is the operating cost for the operators, and this is the capacity for that particular link that's being considered. In these cases, an operator can also consider alternative fleet sizes and capacities, in which case it becomes it's just adding some additional constraints. But you would build in discretely the kind of like frequency design aspect into this problem if you want to. All right, but and all these are in all these costs, travel costs and operating costs, are in units of dollars. Okay, so the idea is that it's interchangeable. So we're looking at how to transfer costs from buyers to sellers, so that they would be willing to make this match. Right? In the case where we have like the dummy, some dummy links, right? These dummy links represent links that no one owns. So in those cases, there's no. We assume that those operating costs are. The operating cost is zero for those dummy links, dummy operators. And this is for the case where people choose not to enter the market. So if the travelers are using other services or staying home, you can keep track of that. So it makes sure the demand is elastic in this case. All right. All right, and then on top of that, we add in mobility on demand services. Right. So we distinguish on-demand service providers from fixed route service providers, and the decisions are a little bit different. So with the on-demand service providers, they're looking at fleet sizing as well as where to place their, where to serve, basically, right? Because you can geofence your service area and decide where to provide service. If you provide smaller area, you would have, for the same fleet size, the wait time would be smaller for travelers, but you would capture less of the market. There's less demand covered, right? So it's a trade-off that you have to think about. So we have those decisions, and there's also access links where there is congestion effect. So people are waiting to be picked up, and so there's these link costs that are congested that have to be considered. Okay. So ultimately, the matching problem that we're dealing with here is a multi-commodity flow problem. In fact, multi-commodity network design problem with congestion. I won't go into like every detail here, but mainly there's an objective that is basically a system optimal assignment objective, where you're considering fixed route travel costs, operating costs, mobility on demand, access times, opening costs, operating costs, and you have flow conservation capacities, demand capacities, and only one link per set of alternatives in the case where you're allowing for alternative fleet sizes or alternative capacities. Right? And this problem is nonlinear mixed integer problem, right? So it's not very clean. And we label this as L1, right? So we solve this once, and let's say we get a solution. If there's corresponding stable outcomes that we can determine to use to determine the pricing to satisfy the user and operator constraints, that would be a successful, like, stable outcome that we can get. Right? So this problem is L1. And let's see. Oops. Yeah. So corresponding to earlier, I showed these are the stable outcome for the original one-to-one problem. This would be the stable outcome conditions for this many-to-many assignment game on the network, where essentially the first constraint set is it's kind of like a generalization of Waldrop's principle, so that the path utility that you gain on the one that you choose cannot be worse off than an alternative path. And there's conservation of utility constraints. There's operator incentive constraints. And all these constraints are linear. And so I can then take these constraints to craft out like the constraint space for kind of similar to what I showed you earlier with the housing example. You can construct a polyhedron or see what's feasible. You can then dictate an objective in here to determine a mechanism to get a specific set of prices, right? Buyer optimal or seller optimal prices. And it's all linear programming, so that's very convenient, right? Okay, so just to illustrate this with a very simple example. In this example, there's no MOD or anything. It's just a couple of links with you looking at two OD pairs. So node 1 to node 4, node 2 to node 4. They have the demands of 8 and 12. And this is the utility that would be gained from node 1 to node 4, and this is the utility from node 2 to node 4. Let me go back a little bit. Right, so under the matching problem, if you solved it, this is the solution that you get, where these are the optimal flows. Oops. There's a bit of, yeah. All right, these are optimal flows, optimal selections of which links to operate. It ends up that this link is not used, right? And so if I wrote out the stability conditions for this particular example, these are the conditions that would then shape out what my payoffs would be. So if I try to find the best case for the operators, these would be the amounts of the fares that they would accept. If I try to benefit the buyers the most, then these would be the amounts. The revenues that you can get, you can then set it as like, what's the buyer optimal set of revenues, what's the seller optimal set of revenues. Under that case, we can see that green operator gets nothing because they don't enter the market. Blue would have a range of $10 to $24 in revenue, depending on how they set the fare allocations. Right? Red is 10 to 10 because they only have one unique pricing mechanism, and so forth, right? And then from this framework, we can then make modifications, right? We can say, what happens if the demand for 1 to 4 increased from 8 to 12, 50% increase? What do you anticipate would happen? And this framework would allow us to then compute the results of this, changing the stable outcome conditions, and you would see that the revenues would now change to, like, for example, green enters the market with a revenue of $1 to $5, and these changes occur. I believe I summarized them here. Okay, so you see that this is the original case, this is the new case, original, new. The changes are for green, they enter the market. Blue, under the seller optimal case, they can gain more potential revenue, but again, it depends on how they negotiate it and decide whether or not they can have more market power. Right? Red loses revenue in this scenario. Right? So the interesting thing is that you can capture the impacts of this demand change on the different operators. Right? When you look at for the different OD pairs, the travelers from 1 to 4 would net improvement in consumer surplus. Right? So you can capture these kinds of changes. So that's the idea behind this model framework. Right? This is how we can use it to look at different configurations of these types of markets, mobility as a service markets. And we can elaborate more on how to model certain things. Right? So I mentioned earlier, you can look at parallel links by considering alternative links and adding constraints that allow you to only choose one of them at most. Right? You can consider heterogeneous population segments by using the S to represent not just an OD pair, but an OD pair and segment. You can look at explicit access and transfer costs. So you can explicitly model those if you're trying to look at access to stations and transfers between stations and different lines. You can look at subsidies for public transit. So in the case where the transit isn't concerned with maintaining positive profitability, you can relax these constraints in the stability outcome for those operators, so that it could be zero, it could be negative, right? So that maybe you just want to ensure a minimum fare box recovery ratio. So there's different things you can do there. As far as the uniqueness, because this is dealing with this multi-commodity flow assignment game, it does have unique buyer optimal and seller optimal vertices, as proven by Sotomayor. The thing with the network case here, though, is the assignment game is unique at the link level, but not at the path level. Right? Something that you can recall from transportation modeling knowledge. The link flows, therefore, can be unique. Ridership per operator, as well as the sum of total consumer surplus and total operator revenue. And so those numbers provide us with metrics for different designs. Right? So we can say, oh, what happens if we bring in another operator into this ecosystem? What happens if if we want to consider subsidizing another operator X amount to reduce their operating costs? What's the impact? And you can look at all those different cases. I mentioned earlier that one of the stability constraints that we showed is essentially a generalization of Wardrop's principle. So if we take the set of operators and set that to the null set, certain variables will drop out of this constraint. And what you see here is essentially the constraints corresponding to generalized Wardrop's principles with known utilities. Right? So given known use of S and link capacities, these would be corresponding to that. Right? So in that sense, we show that this is, in fact, a generalization of the network assignment that you have traditionally used in transportation planning and modeling, but now it's broadened to consider multiple operators and their interactions. One challenge that we noted when we developed this was that it's possible to have an empty core, meaning you can end up with an assignment solution that has no stable outcome for the cost transfers. So that's problematic. So basically, we actually show a counterexample to illustrate that it's possible to end up with that kind of case. Right? So how do we address this? Right? Because now this implies that if we just solve the model, the matching problem, we're not guaranteed to get a stable solution for that system optimal assignment. So that system optimal assignment may not be attainable, right? And so to deal with that, we define a modified version of L1, which L1 is the problem that I mentioned earlier with the matching problem, where we add the constraint of requiring that the stable outcome space to be non-empty, right? It's an implicit constraint. We don't explicitly add it to the matching problem, but we add it in the algorithm for solving this model. Okay. So as an example from earlier, I didn't show you the details, but if you were just to assign this to the system optimal with L1, you would get z equals 3480, but it's not stable. But in the case where you find a worse solution, there's this solution that is stable, but the objective value is 3680. It's a little higher, right? So now this MaaS platform equilibrium is finding this solution, right? L1C. And so how do we get that? Algorithmically, we use integer programming algorithms like branch and bound, and we try to take advantage of the structure of the branch and bound algorithm so that when we're branching and solving our solution, if we end up with a solution that is not stable, we try to find ways to deal with that. Okay, so I won't go into too much detail with this, but basically stability is necessary but not sufficient, and so it still could get stuck, and a solution may also be stuck at a branch. So there's different considerations that have to be made that such that we ended up having to add in a subsidy decision that the platform can have. So like basically it's possible that the best solution that you can find might be to say the agency or the platform would provide an explicit subsidy to ensure that what would have been a non-stable solution would now become stable. But it's at a cost, right? Because you're subsidizing. So we explicitly put in that subsidy cost. And so you can end up with a solution that is an equilibrium, but it depends on whether or not you have subsidy incorporated into there. Okay. So and so the subsidized equilibrium, we call it L1S, right? So there's L1, L1C, L1S, and this is I won't go into this in detail. Just this is the model that we use to find the subsidy by minimally perturbing it, so that we're not putting as much costs as we need to. Okay, so the algorithm that we end up with, branch and bound, if we're just solving L1, we can get it exactly, given time. It'll converge to the exact solution. But as I mentioned, getting L1, we do not guarantee that it's stable. So we also present a variation of this algorithm that captures getting a solution that we will always get an equilibrium solution, but it might not be the best equilibrium solution. So it's a heuristic, right? It's very messy. So basically, it's a branch and bound where each branch you relax your binary constraints for which what links or zones you're selecting, and then given that relaxation, you solve essentially like a Frank-Wolf algorithm for nonlinear programming to get some solution, and then you decide whether or not that has a stable outcome or not. If it does, you're good. If it's not, then you have to consider maybe subsidizing in that branch, and then you continue branching because you're not guaranteed to. That might not be your best solution. So in terms of branching, you're still using the L1 objective value to cut branches. All right. And we show that the heuristic there's always a worst case risk solution we can get. So it's basically taking the L1 solution and adding subsidy to that. So as long as whatever solution we get, it should at least be as good as that or better. Right? This algorithm is available open source on GitHub. This is work that my PhD student Bing-Ting Liu had done for her dissertation, and now she's starting at UCLA, right, as a postdoc. You're welcome to make use of it. If all branches are stable, the solution found is an exact optimum, as I mentioned. If one of the branches are unstable, the best solution found is then one of these two cases, which depends on whether or not there's subsidy involved. And I provide a small illustration before I'll stop there, and then lecture 2 will continue discussing this in a little bit more detail in terms of applications and brainstorming. Right, so in this case, what we're seeing here is there's essentially 4 zones, right, where A, B, C, D, but you have a bunch of alternative operators that also visit other nodes. You're also considering these dashed lines represent routes that on-demand service providers are considering to provide. So like if this is open and this is open for the light blue, then they're serving travelers between those 2 nodes. Right? And there's a congestion effect in place for those, for people waiting for those services. So when you expand it out, this is what it becomes, from this to that. And the solution, it turns out, is stable. So L1 solution is stable in this case. So ZL1 is equal to ZL1C. It's this number, and these are the flows that you see here. The output here ends up, operator 7 operates 1 vehicle fleet. And this graph shows the seller optimal and buyer optimal vertices, the values for the stable range. So basically, any pricing that they set that falls between these values should be a stable set of pricings corresponding to this assignment. Okay, so we're able to see like which lines are being operated. These are the flows that are being served, right? And we can summarize all the high-level metrics, right? So basically, we see operator 1 having these potential revenues, depending on, again, buyer or seller optimal. Typically, if the platform is a public platform, like a public agency, they would probably go with something more towards buyer optimal, right? And then, yeah, some of these are not operating, as you see. And then 7 to 9 are MOD operators, and you see only 2 of them are operating. Right? So it lets us really capture all these different flavors and make trade-offs between different scenarios. Okay, so I will stop here. So basically, yeah, we've developed an algorithm to obtain mobility as a service equilibrium conditions that can include platform subsidy to ensure that outcome is always stable. And what it does is, given the potential network structure, right? So we can look at potential network structure like candidate locations or candidate routes that are being considered. So it's a little bit like a network design, but it's a network design game, cooperative game between different operators in this multimodal setting. And considering different capacities, fleet sizes, and demand patterns, you output these outcomes. Okay. And again, the algorithm can be found in this QR code. Any questions? I'll stop here. Yeah.
Any questions? Compare with the market here, we focus only on the buyers and the sellers.
Yeah.
Maybe in transportation, sometimes we pay more attention to the process. So I want to know, do you think it is possible to extend your MaaS equilibrium to a dynamic equilibrium in the field? And if so, how can we guaranteeing the uniqueness of the solution?
Yeah, that's a great question. So it's certainly, I think, making it into a dynamic problem setting can be doable. But yeah, you might lose those properties like having the guaranteed stability and things like that, right? So even in conventional traffic assignment, going from static to dynamic, it leads to those kinds of challenges. But yeah, it should be feasible. I mean, we try to simplify some things, but other things we kept more complicated. You could also simplify things like maybe not have capacity constraints and only consider congestion effect everywhere as a way of interpreting capacity. Right? You could potentially only have capacity and not congestion effects. Right? So you can modify. The framework is flexible in that sense for you to play around with, and I encourage that. So I think if you're interested in extending that, I would love to work with you to discuss more. All right. Thanks. Yeah, and before you guys have more questions, so the next lecture I'm gonna go more in detail with examples, subscription plans, and then I want to do like a brainstorming session of different applications of this framework. So for that brainstorming session, I want to invite you guys to discuss with me and see how we can turn this into TRB papers. So, other questions?
Thank you for your presentation. So actually before the question, I'm not familiar with the mathematics that much, but
Okay.
yeah, I think depending on the demand scale, like especially temporarily different, the optimal values can be changed. So if you want to implement that algorithm into real world, is there any proper duration for the optimizations or some maintenance of the systems?
Yeah, that's a great question. And so first off, with regards to mathematics, that's particularly why I shared the GitHub for the code, so you don't need to have to dive into the mathematics. You can just apply it. But as far as the duration, I think you're referring to how scalable is it, or how long do you want to run? This is a planning model, so the intent was to make it. First, we want to start with exact solution methods, or as close as we can to the exact solution methods, or at least bounded heuristics. It is quite slow, and you'll see more in the next lecture how slow it can be. So the way that we're actually modifying this now is we're looking at stochastic cases where we don't even have to enumerate the paths. So we're taking advantage of some new techniques so that you can scale it much more easily. But the Sioux Falls examples that I'm going to show later on, they can range from less than half an hour to 10 hours because it's an NP hard problem. And so the duration can be long. So you can cap it, all right? But the solution you get might not be that interpretable in that case, unless you have unless you find a solution that is already feasible to other conditions.
Thank you.
Yeah, I would like to ask how you measure the travel cost of the link.
The travel cost of the link.
Yeah.
So the travel disutility is the travel time and basically all the non-out-of-pocket costs that they might incur. Right? So costs that they have to pay the operator, we capture that through the fare payments.
Yeah, and also would it be possible to incorporate the MaaS resilience, network resilience as one of the indicators too?
So you're saying use resilience as an objective?
Yeah.
You could, right? So basically, I would say that the matching problem objective is to provide a system optimum case, but I think for the resilience part, you might want to consider that in the design of the prices, so that you're making sure that you capture the incentives of the users, but also if you have something that you want to maybe enhance redundancy, increase resiliency,
Yeah.
you can set the prices to incentivize people to make use of those.
Thank you.
That's a good idea. Maybe it's something that we can talk more about.
Okay, let's take a break and let's come back at 4.